Welcome back everyone, my name is Dustin, and in this video we're going to go over object-oriented programming and to see if we still need it when using modern C++. OOP, or object-oriented programming, is one of the most debated topics in C++ programming. Some say it's outdated, other people swear by it, but what if I told you that there's a modern approach that makes polymorphism safer, faster, and more flexible? Alright, so let's get started. So let's start with a quick object-oriented refresher. Object-oriented programming, or OOP, is built on four main principles: encapsulation, bundling data and behavior inside of a class, abstraction, hiding implementation details from the user, inheritance, creating a new class from an existing one, and polymorphism. The last one, polymorphism, is where things get really interesting in C++. The traditional way to achieve polymorphism in C++ is through virtual functions. So let's do an example. So first thing, let's create a class. This is going to be our base class, and we'll just call it animal. And this is going to just have public stuff. We're going to have a virtual destructor. That can just be default. And we're just going to have a pure virtual function for speak. This can also be const. And to make it pure virtual, we have to say equals 0. That means that any base class that inherits from animal must override this function. Okay, and let's create two classes. We'll go class dog. It will inherit publicly from animal. And this will just have a public section. And we'll say virtual void speak override. Oh, that's const. Well, const override. And this is just going to be std cout woof. Cool. And let's just copy this whole thing here and paste it and just create a cat from it. So we have a dog and a cat, and both are animals. So we're gonna do two simple examples of how this works. Let's make a make sound function, void make sound, and this will take in any animal, const animal, reference animal. So this is using polymorphism because it's taking in any animal and it's going to run its speak function. Animal speak. And let's create another function just to run all that in. I'm going to try to keep everything on the same page here, or in the same file. So let's go void basic OOP behavior and polymorphism. Cool. So we're just going to say, let's go up here and let's add some more includes. And for our includes, we're going to include vector. So we can have a container or a vector of animals. And we're going to use memory because I want to have unique pointers to animals. Okay. And let's go back into our function here. And let's create some animals. So we'll go std vector of std unique pointer of animal. And all these animals. Awesome. So let's add some animals to our vector here. So we just go animals dot pushback std make unique animal, but we don't want to do animal because that's going to be a abstract or a base class. We want to go dog, and then we also want a cat. Cool. You can add more animals if you desire. Add more animals if needed. Cool. And then let's just say std cout and just have some separators here. Then we'll say calling speak for each animal. Copy this line, paste it down. And all I want to do is loop through these animals. We'll go for const auto reference animal in animals And all I want to do is say animal speak. So what this is going to do, this is going to call the derived class method. So let's copy this here and go to our main and run this here. So if we run this, cool. As you can see, we call woof and meow. Why? Because we have a cat and a dog, and we're just going through and it's calling the underlining, the actual derived classes speak function. Oops. And let's try something else. So that's just calling the function directly here. Let's call this make sound. And for fun, we're going to use std ranges to do that with 4 each. So let's do this here, copy that, get rid of this at the front because I had an unnecessary gap. Cool. And we'll change this to calling make sound using ranges. And I'm going to want to come up here and include algorithm. Now we could just call this function inside of here and pass in the animal, but I want to do it this way just to show some different things that you can do with modern C++. So we go std ranges, and then I can say for each. Now you pass in the container animals, and then we take our lambda, and it's going to be auto reference animal, and then I'm going to want to call make sound on the dereferenced animal because we're holding pointers. So what this should do, it should loop through each animal and basically do the same thing, but using ranges and calling this function. This function we'll call animal speak. Awesome. So it did the same thing. That's great. So how is this working? The base class animal has a pure virtual function, speak. And each derived class has to override that. And then through dynamic dispatch, this determines which function to call at runtime. But how does C++ know which speak function to call at runtime? That's where the vtable or virtual table comes in. When a class has virtual functions, the compiler creates a hidden lookup table called a vtable. This table stores pointers to the actual function implementations for each derived class. Each object with virtual function also has a hidden pointer called vpointer, and that points to the vtable of its class. So this would be an example of a vtable layout. So for each class, it has a vtable, and it also has function pointers. So the animal class has the speak, which is a pure virtual. Then the dog class also has a speak, and it will point to the dog speak. And then the cat will also have a function pointer that will point to the cat speak. So it knows how to find this at runtime. So what happens at runtime? When we call animal speak, it looks up the vtable of the actual object type. It retrieves the function pointer stored in the vtable, then it calls the correct function, dog speak or cat speak, in this example. So what are some pros and cons of virtual functions? Well, let's first talk about the pros. It's extremely flexible. This works with any derived class. It's also very extendable. New classes can be easily added in. You just have to add the new class and inherit from the base class. What are some of the cons? There is overhead. This requires a vtable and virtual table lookup. It's tightly coupled. Derived classes must inherit from the base class or a common base class. And then it is not compile time safe. A lot of issues can happen, like missing overrides that appear only at runtime, or take Unreal Engine for instance. Sometimes you'll forget to call the super of that function, and a lot of stuff will be missed out because even though you derived from it, you still need to call things from the base class for initialization purposes and other reasons. So now that we understand vtables more, let's explore some faster and safer alternatives using std variant and C++20's concepts. So what if we could avoid vtables altogether? A way to do that is using std variant. Let's go up to the top and let's include variant. So include variant. So now we're going to want to create basically the same classes here, dog and cat. However, we don't want to inherit from animal anymore. So let's bring this down here and we'll go paste these down and we'll just change these to doggy. Remove that, change this, change that. Change cat to kitty. Same thing, we have to remove all that stuff. And once we have these two classes, they both have speak functions, we can actually create an alias to animals using std variant. So we can say using, and we'll just call this var animal is equal to std variant of doggy and kitty. And then we can take the make sound function again, copy this, paste it in here, and just change it. Instead of using an animal, we're going to use a var animal. But we can't just call it this way. What we're going to need to use is something called std visit. So what that will do is it will go through and it will find the functions that we need. So we go std visit. That takes const auto reference a dot speak. And then this has to take in the animal. So what std visit will do is it will go through all the types that it has to for based on the type that we pass in and call its speak function for you. So if it's a dog, it'll call dog. If it's cat, it will call the cat. All right. So let's add it, make a new function, and we can go void OOP behavior using variant. And we can say var animal my dog equal to doggy. And my cat is equal to kitty. And then we can call, let's actually copy this here. And we'll paste this here. And then we can change this. We'll say calling speak for each var animal. Then we can say this is using std variant and std visit. Then I can go make sound and send in my dog and then my cat. And then we're going to have to bring it down here and we can say OOP behavior using variant. Run it. Let's comment this one out. Wonderful. So all that did was it looked at the variant, which one it was. So it was a dog. So it knew to call the dog speak. And then the second one, it was a cat and it knew to call the cat speak function. Pretty straightforward. Why should we use std variant? Well, there's no virtual function, so no vtable overhead. It's memory efficient, stores only one type at a time, and then you have compile time safety. So it will catch missing cases at compile time. You don't have to wait till later on during runtime. It was automatically caught. There are some downsides to using std variant as well. It's less flexible. You must explicitly list all possible types in the std variant. So that's one of the biggest issues. So say you want to have many different animals. So in our var animal here, we would have to keep adding in more. So like bear, snake, etc. Right? Like whichever animals, you got to keep adding to it, which it might not be bad, but sometimes it can become very tedious with many different types. So what if you need the flexibility without the cost of virtual functions? Well, that's where C++20's concepts come in. C++20 introduced concepts, a game changer for writing safer, more flexible, and faster generic code. But what exactly are concepts and how do they replace traditional polymorphism? Concepts are a way to constrain templates so they will only work with compatible types. Concepts also check at compile time whether the type meets the specific requirements. Let's do some examples. So first we'll use a template, and we'll do a template without concepts. So we'll say template without concepts. We can say template type name, then void make sound template. Const t reference animal. Bring this down, and we'll say animal dot speak. Now this will only work if t has speak. But let's make another function. So they will say void OOP using templates and concepts. And let's go up here and we'll copy all of this. Bring this down. And let's say calling speak for each just regular animal that we pass in. This is using a template. So we can say make sound template. And we can do the same thing. We say send in a dog, and we can send in cat. So if we copy this is without concepts. Right now we're just using a regular template. And let's comment this out and paste that in. Get rid of the void there. Cool, and run this. So this works the exact same way. So it's taken in and knows to call speak. But what happens if we have a struct that doesn't have the speak function, or a type that doesn't have the speak function? So let's go struct, or we can say class. Sure, we'll just maintain the same way. Class, and we'll say car. And it has a public. Instead of speak, it has honk. Const std cout honk. And if we try to call a car, well, if you look, right now it's not giving us any errors. Why? Because we have to try to compile it first. So if we compile it, it doesn't work, and it says speak is not a member of car, which is true. It is not a member function of car. So what if we could have this have an error before we even try to compile it? So we can improve this template by using concepts. With concepts, we can enforce that only valid types are allowed, and the compiler will give a clear error, and will most of the time, especially if you're using Visual Studio, give you the error before you even try to compile your code. So let's go up and let's include concepts. And let's make a concept for an animal. And we'll just do that. We'll do that right under this template. So what I want to go is template, type name, T. And I'm going to say concept, animal concept is equals requires T. Then it has to say a dot speak std same as void. So what this is saying is, whoop, that should be a semicolon, that T needs to have a speak function and it must return void. Okay, so this is required. And then we can create a new template. We can go template, animal concept, T. Then we can say void make sound concept. Const T reference animal. Animal dot speak. And this is your compile time polymorphism. Cool. Let's go back into our function here and let's copy all of this again and paste it down here. And then we'll say calling speak for each animal. This is using a template function with concepts. Change these both to concept. And that should work as well. So if we run this, it should work the exact same way. Awesome. So it works with concepts. It also works with templates. However, say we copy this here and paste this in and remove this. Remember, if you see with a regular template, it doesn't do anything. But if I change this to concept, it automatically gives us an error. And it says no instance of function template make concept matches the argument list. Arguments are a car. So it automatically is telling you that this does not work with a car. So if we comment that out, that's fine. Everything should be okay. So how does this work? The animal concept checks to see if a type has a speak function or a speak method that returns void. If the type doesn't satisfy the concept, the compiler gives a clear error message. The function will only work with valid types, preventing runtime issues. So why would you use concepts? Concepts have zero runtime overhead. Everything happens at compile time. There's no base class required. Works with any type that would have, in our case, any type that has speak. And it actually has very readable error message. If the type doesn't meet the requirements, it will automatically not let you use the function right away. So you automatically get an error. And the compiler will tell us this immediately. But when should you use concepts? Take a look at this here. So there's a use case. So if you need runtime flexibility, you might as well stick with virtual functions. That would be your best approach. Need compile time safety, you're going to want to use concepts. And if you need a fixed set of types, you might as well use std variant, because that'll save you with the overhead as well. So if you want fast, flexible, safe polymorphism without inheritance, concepts are the way to go. Are there some drawbacks to using concepts? Of course. There's always a give and take. With concepts, you cannot store multiple different types in the same container like you can with base class polymorphism or std variant. You can hold different types in one variant. However, you can store different concepts inside of a variant. Let's take a look at an example where I ended up using this in Scion 2D. All right, so in Scion 2D here, I'm using a concept as for the command interface to ensure all structs and types pass into the command manager as necessary undo redo functionality. We end up creating a concept, and it's called a concept type. These functions must have undo, and they must have, or these types, whatever type is passed in, must have undo and redo functions defined, and they must return void. And then what I do here is I create var commands using std variant, and the command types is a variadic amount of command types. So all these var commands must be a command type. Now with this, same with this, with undo, redo, and command manager, you can use your original polymorphism as well. This is just something I wanted to do just to get a better understanding as well on how to use concepts and how to try to get away from using virtual functions. Let's take a look at the pros and cons of each thing. So if we have virtual functions, the pros for virtual functions are they're very flexible. Cons, vtable overhead, and you can also have runtime errors. If you take the std variant approach, there's no vtable, it's faster, and it offers compile time safety. However, it's a fixed type set that can't easily be extended without changing the code, the direct code. And then if you take the concepts approach, the pros are zero cost, works with any type, and is safer. However, there is no runtime flexibility, and you can't store it in a container unless you use the concept std variant that I showed you before. So all in all, if you need runtime flexibility, stick with virtual functions. If you want performance, try out std variant. And if you prefer zero cost abstractions, then concepts are the way to go. So what do you think? Do you still use classical polymorphism in your code, or have you switched over to the C++20 alternatives? Drop a comment below, and don't forget to like and subscribe. And also let me know if there's any topics you want me to go over. And that's it. Take it easy.